For much longer. We're going to finish this booklet today. Once we get to the end of the booklet, there's some questions. I will let you guys come up. You can see your mark. There are still a couple of students that have not sat the test, which means you will get it back in our next lesson. Okay? Now, we've spoken about diffraction quite a lot. Please stop talking. Hugo, Josh, can you close it, please? Can you close it, please? Yeah, I'm trying to teach. Close it, please. Josh, close it, please. All the way. Thank you. So, we've got all of these different wave phenomena. You need to know the definitions, be able to draw diagrams. So we've done reflection, refraction, now diffraction. We have spoken about it. It's the bending of waves around objects or the spreading of objects as they pass through a gap, okay? The frequency, obviously, it's a gap or an object, so it's still in the same medium. It's not speeding up or slowing down, so frequency and wavelength stay the same. So here you can see this nice little diagram. This pretty much explains why I can hear that silly bird squawking outside, right? The sound waves, thank you, Hugo. The sound waves are diffracting through the door. Now, when we're talking, remember we spoke about the frequencies that we throw out of our mouths is around about 50 hertz to 100 hertz. So if you think of the wavelengths, they're actually quite large, okay? Large wavelengths tend to diffract a lot. So just remember that. If your wavelength is bigger than the object, it's going to diffract a lot. If the wavelength is bigger than the gap, it's going to diffract a lot. Okay? So that's what I've got here. If it's bigger, it's going to diffract more. And so there's no equations for diffraction, but there are a ton of diagrams. So let's get on with here. I've made two gaps. We've got a wavelength that's equal. The wavefronts for both diagrams are approaching both gaps. Essentially, with the small gap, if the wavelength's bigger, we're going to get more diffraction. Okay? So in this diagram here, you need to be able to draw. Now, you've got to be careful. This is Huygens principle. So we're not going to draw them as large. It's not going to do that. We're going to get the spherical wavefronts traveling out. Now, I'm just going to cheat and I'm going to sketch in an angle to show how far. That's just my little cheat to know where to stop my wavefronts. Okay, so if you could do the same. And then with this kind of question, you've got to show the diffraction is larger, you've got to show the wavelength stays the same length, and then you have to draw your spherical wavefronts. Okay? So try and do that as best as you can. Whoa, let's try that again. Okay. Then over to the other side, the wavelength is now smaller than the gap. Okay, so we're not going to get as much spreading. So all we need to do to compare here is probably draw in one more wavefront because it's missing. Let's just draw. There will still be some diffraction, just not as much. Whoop. I'm sorry that I'm boring you, Hugo. So there, if you look at Huygens principle, the mathematics behind this, it's incredibly complicated. So that's why we just go to diagrams. There's the calculations are way beyond a year 12 level. But anywhere, don't draw this, but anywhere you stand, you're going to get this, the rays are going to split out. Because remember, Oopsies. It's as though there are new wavelets, secondary wave sources at the gap, which then suddenly spawn into existence, and then they interfere with each other. And that where they interfere, that produces the next wavefront. Okay? So there's plenty of diagrams out there. There's animations that show this. Oops, I'm going the wrong way. So, just there. Oh, here we go. Here we go. High frequency tend not to bend as much around obstacles and gaps. Which explains some phenomena. Have a think. You're approaching a party. It's down the street. The frequencies that you are going to hit, you cannot see the party yet. There's trees and cars and buildings in the way. But you can hear the... Those are the bass, the low frequency, long wavelengths. Long wavelengths diffract more. All right? So the long wavelengths are going to diffract around the buildings, around the trees, around the cars, and they'll get to your ears. Okay? As you get closer to the party, you start to hear the... Darude stands for... You hear the higher frequencies. Okay? Because as you approach the house, now there's going to be more... Well, you're closer to it, there's less objects in the way. Okay? Now have a think, as I said, the lower the frequency, the more the diffraction. That's why at harbours and at docks and at industrial areas, your ship horn, your fog horn, think fog, because you can't see the ship, is going to be very low. If the ship's coming into harbour and you can't see the ship because there's this big shipping container in the way, you might need to be able to hear it. Alright? So if the ship was putting out a beep, you might be in a shadow, you might be behind a building, you're not going to be able to hear what's going on. Alright? Next, police sirens, ambulance sirens. They go wee-wah, wee-wah, wee-wah. Yeah? And sometimes when they approach an intersection, what do? Anyone? And they change their siren. The wee-wah, wee-wah is because the ambulance is travelling through past various objects, big objects, small objects, trees, trash cans, people. So it's doing a big swath of frequencies. So you're going to hear it wherever you are, whether you're in line of sight or whether you're behind a building, you're going to hear it because the lower frequencies are going, longer wavelengths are going to diffract to get around to you, okay? Next. Now, these are just a few examples, and I don't think they'll be in the test, but this now might explain things that you've maybe thought about from time to time. Tweeters, they're the little speakers that go up on the front of your speakers next to your TV. They've got to be in the line of sight because they're the ones that are tweeting out the higher frequency sounds. Whereas the subwoofer, you can throw it behind your cabinet, behind the couch, because the bass is going to diffract through the entire room. Okay? So, let's go over the page. That's right, you've already seen it. Speaker in a room is playing some savage dubstep. Person walks down the hall. Now, we've been given the size of the door, okay? We need to figure out the wavelength, okay? So let's find out the smallest wavelength. So we'll take V equals 342 because my previous sums. So the maximum frequency produces the minimum wavelength. And then we'll do the same for the maximum. We'll find the minimum frequency. Okay. Now, there wasn't really any point of doing that because we know that the lower frequency has the longer wavelength. In fact, I'm just going to color code these. I'll try my best to draw this. Let's draw the short frequencies doing this. Now, they're going to diffract a little bit. Now, I'm going to put my cheat lines in here just to help me draw the diffraction, okay? Now, I've just set a scale that's 0.2 of a meter, and now I've got to draw this as 15 times longer, or 20 times longer. I'm not really going to draw that to scale, but let's just draw in blue further wavefronts that are further apart. So we'll draw our blue ones. And then when we get to this gap, again, I'll just draw my cheat lines like so. Okay, something like that. There have been questions in past test papers about windows that have been rolling up. And there's a sound coming into the window, and as you roll up the car window, what would you hear? Because obviously that's a pretty tricky question. You're changing the length of the gap. And so when you get to, typically maximum diffraction occurs when your wavelength is equal to or greater than. So if you're going past the wavelength, you're going to start to make it diffract. But let's look at this. If this bloke's walking from point A to point B, would anyone like to think about what they would hear? Yes?
You're going to hear the max or the lower frequency first.
Yeah, then what?
And then the high pitch, like everything.
Good. You corrected yourself. Because the lower frequency is still there when he's directly outside the door. Then?
And then you just hear the high frequency.
Exactly. It's like you weren't invited to the party, so you just you walk past the party and you have a look. And you look at me. So the high frequency sounds disappear, but you can still hear the doof doof. Okay. So just put that into a couple of sentences for me, please. Now, remember, test, week 4, Tuesday, in class. There will be I can't even remember, I made the test Christmas holidays last year. There will be a wavefront diagram, right? And it's going to either be refraction, reflection, diffraction. What else is there? Where else have we drawn wavefront diagram? Huygens principles, okay? So there will be some kind of diagram. That's about it. Now, is that as much as we done now? I think we're finished. Okay. Sorry? Then low frequencies again, only. Okay. Cool. I'm just trying to think. Light can diffract. Actually, let me just open up that new PHET applet. Yeah, I don't know what it stands. Physics, engineering, tech, something, I don't know. Again, guys, open up, if you haven't, you can open up the Falstad applet and this applet, play with the applet, change the different variables and see the effect. Also, the Falstad applet demonstrates all of these. As we saw, it does reflection and refraction and dispersion. It does heaps. So if we go back to diffraction, light, here's the thing. Light has obviously, I don't know if we really cover light this year, it's got a really small wavelength, okay? So green light, 500 nanometers, that's 5 times 10 to the negative 7 nanometers. What just happened?
Your keyboard showed up.
Huh?
Your keyboard showed up like.
Oh, did it go away?
Yeah.
Good. So, in most cases, the object is much, much larger than the wavelength. That is why I can't see Matthew Gamble, because there's a bloody great big object in the way. And the waves of light coming from Matthew Gamble's head are much, much smaller. The gap, it's too big, okay? So it won't diffract around. What we need to do is get really, really small objects, okay? And I want to show you this really cool demo, and then it'll make more sense next week and the week after. But we can, a human hair is on the order of 100 microns, which is about 100 micrometers. And so we can split a beam of light with a human hair, and it will actually diffract around. And I'll show you that while you guys are working on these questions. But let's just quickly look at, if we had a spherical object, fire our laser pointer, and if the object, look, 100 microns, that's the diameter of a human hair, okay? And so we're going to explain this. This is a very weird pattern. Okay, Thomas Young in the late 1700s shone light and looked at this, and basically was able to show that light acted as a wave, because basically it splits the light into two sources. They diffract around, and then they meet back on the screen. But by splitting the beam into two, you've now got two separate wave sources, and they would interfere with each other. And so where a crest meets a crest, you would get constructive interference, you get a bright spot, and then where a crest meets a trough, they would literally cancel each other out. I'm about a lesson or two ahead of where we currently are. We're going to learn about this next week. But the dark rings was destructive interference, where the wavelength, they were out of phase by 180 degrees. We've learned about phases. Then the next band here, we're back in phase, we've got a crest and a crest. So I'll grab the laser beam, and I think Hugo's already sourced a hair from Josh. No? Didn't one of you guys pluck a hair? I thought I saw you guys. No?
This is strange.
Well, I was talking to... Neither do I. I was talking to the class, and in the corner of my eye, I thought I saw you guys plucking hairs. I don't know. So, yeah, I know, this is getting weird. Guys, could you please, that's pretty much the booklet done. Could you please answer the questions at the back of the booklet? All right, I'll go grab my laser pointer. Then once we've done that, you can come up and I'll show you your test result, and you continue with your marks, with your questions.